We've been talking about trigonometric substitution lately, and I want us to extend this idea. I want us to now talk about hyperbolic trigonometric substitution. And what you're going to see is that the process is virtually the same. But instead of using circular trigonometric identities, we're now going to use hyperbolic trigonometric identities and use those in order to solve some definite integrals. Specifically, I want us to show that in computing this area over here. So this area is defined as the region between this hyperbola here, x squared minus y squared is equal to 1, and this line coming from the origin to a point along our hyperbola, and we parameterized these with t, so this is cosh of t and sinh of t, and also our region is bounded by this x-axis. So this whole region here in yellow, we want to find its area. And in order to do so, I want you to try to pause the video, set up a definite integral for this, and then use a hyperbolic trigonometric substitution in order to compute it. So pause the video and give that a try. All right, assuming that you've given it a go. Again, I think a good place to start is to wonder, okay, how do we want to ultimately integrate this? Do we want to integrate it with respect to x, or do we want to integrate it with respect to y? And I'm going to say that we are definitely going to want to integrate this guy with respect to y. And that's because we only need to set up one integral then. If we go in terms of x here, we have to set up two integrals. So hopefully that will save us some time and work. Now, if we're going to integrate this guy with respect to y, I think a next good step here would be getting an equation for this line down. Let's start to describe what that is. So the equation for our line here is going to be y is equal to, and then we're going to have our slope, which is going to be rise over run. So that's going to be sinh of t over cosh of t times x. So that's the equation for our line. And now we can start to throw together a definite integral. So let's get a definite integral going. And this is going to be, if we're integrating with respect to y, that's going to be from 0 up to this y coordinate here, which is sinh of t. So this is 0 to sinh of t. All right. And then our integrand is going to be the distance between this hyperbola and our line. So that is going to be, first, I guess we need to get this guy in terms of y. So let's get this hyperbola in terms of y. So this is going to be x squared is equal to 1 plus y squared. Taking the square root of both sides, we have x is equal to plus or minus the square root of 1 plus y squared. And again, we only want this positive root because x over here on this right branch is positive. So we have this positive root. Let's plug that in. Square root of 1 plus y squared. And then we want to subtract this over here in terms of y. So let's get this equation of our line in terms of y. And that's going to be cosh of t over sinh of t times y is equal to x. So let's plug that in. We have minus cosh of t over sinh of t. And then this is times y. And then we're integrating all this with respect to y. So this is our definite integral, and it looks quite big. And again, I mentioned earlier, we want to ultimately use hyperbolic trigonometric substitution. And before we start doing that, just a few things to note here. Sinh of t, cosh of t, and this sinh of t here, they're all constants. So we are integrating with respect to y. So these guys, cosh of t, sinh of t, they are just going to be treated as constants. So that's one thing to remember. Secondly, before we make any sort of mention of a hyperbolic trigonometric substitution, I think we can simplify this problem. We can split this integral up into two smaller integrals. I think that will make our lives a little easier. So let's do that. So let's do a purple integral. This purple integral is going to be the definite integral from 0 to sinh of t, and it's going to be the square root of 1 plus y squared. And then we're integrating this with respect to y, and then we'll subtract, and we'll keep this guy. Let's do another integral in yellow. So definite integral 0 to sinh of t, and then this integrand is going to be cosh of t over sinh of t, and all of that multiplied by y, and then integrating that with respect to y. So these are our two definite integrals, and what's nice is that we can already solve this definite integral in yellow. This one's actually pretty easy to solve. So again, cosh of t and sinh of t, those are just constants. So anti-differentiating y, that is just going to be y squared over 2, and we'll keep these constants. So cosh of t over sinh of t. All right. And then evaluating these at our limits, that is from 0, that's 0, and that's sinh of t. So what do we get here? What do we get here? Evaluating at our upper limit, we're going to have sinh of t, and that whole quantity squared. And then there's a sinh of t down here, so we're going to get rid of one of those. And we'll still have that 1/2. And then looking at our lower limit, that is just going to be 0. So 0 times something else, that's just 0. So it looks like we're going to be left with 1/2, that 1/2 there. And then we keep our cosh, so that's cosh of t. And then we lose 1 sinh of t in this numerator here. So this is sinh of t. Sinh of t. So this is what we get after evaluating this definite integral in yellow. And what we're going to do now is tackle this definite integral in purple, and then we'll have to remember to subtract what we got over here. So let's tackle this definite integral in purple next. And this is where we're going to start to talk about a hyperbolic trigonometric substitution. And what we need to note is this. If I didn't tell you like, oh, you want to use a hyperbolic trigonometric substitution, you'd probably say, oh, I definitely want to use a trigonometric substitution. And I'm probably going to want to use the fact that tangent squared plus 1 is equal to secant squared. And that you can try to play out, it's going to get a little messy. I'm just going to warn you of that. So what we want to use, I gave you some tools up here to help you out, some hyperbolic trigonometric identities, and we're going to want to use this guy right here. Mainly, let's add sinh squared over. So we're going to have cosh squared. Cosh squared is equal to 1 plus sinh squared. And again, this is a hyperbolic trigonometric identity. So let's use that. Let's make a hyperbolic trigonometric substitution now. Here we go. So we're going to let y be equal to sinh of u. Okay? So that is our hyperbolic trigonometric substitution. And then integrating both sides, dy is now going to be equal to derivative of sinh, remember, is just cosh. We talked about that earlier in a past video. So derivative of sinh is cosh. This is cosh of u, and then we have du. And lastly, I think we can get some new limits here as well. So maybe I can put those in green. So our new limits of integration are going to be what? Our upper limit here. So let's look at our upper limit. Make sure we get these right. Our upper limit, we're told y is equal to sinh of t. So plugging this in, we have sinh of t is equal to sinh of u. And we can see now that u is equal to t. So that's our new upper limit. And then looking at our lower limit, what do we have? When we plug in 0, it looks like u is just going to be 0. So we like that. Now we have our new limits and we have our hyperbolic trigonometric substitution. Now we can put all of those things together and make our new definite integral. So let's do that. Here we go. So maybe we can go back to purple here. We're going to have the definite integral now from 0 to t, and then our integrand. So let me scroll up just a touch. Here we go. So the square root of 1 plus y squared under our substitution now is going to be the square root of 1 plus, and we have sinh squared. So this is going to be sinh squared. Sinh of u, that whole quantity squared. And then we have to substitute again for dy. So dy is cosh of u du. And this is our entire definite integral. And now, similar to what we do with regular trigonometric substitutions, the whole reason why we did this is to leverage this fact. What is 1 plus sinh squared? 1 plus sinh squared, if we scroll back up, right here, we said that that is cosh squared. That is cosh squared. So we get cosh squared in here. This becomes cosh squared. This becomes cosh squared. Taking the square root of that just gives us cosh, and multiplying by another cosh, we have the definite integral from 0 to t of cosh of u, that whole quantity squared, and then integrating with respect to u. And now we can use yet another hyperbolic trigonometric identity. We're going to use this full arsenal I gave us up here. So cosh squared is what? Cosh squared up here I said is going to be cosh of 2u plus 1, and then that whole quantity divided by 2. So let's rewrite this definite integral under that, and we're going to get this. So definite integral 0 to t, and we said that this is cosh of 2u plus 1, this whole thing divided by 2, and we're still integrating with respect to u. So now let's anti-differentiate and see what we get. So this is going to be sinh of 2u over 4, and then plus 1/2 u. And then we can evaluate at our limits, and we get what? Well, you can see the sinh of 2u, similar to how we deal with these in regular circular trigonometric functions here, we are going to leverage another hyperbolic trigonometric identity. I know, we're racking them up. So what is this? This, if we scroll back up, I told you that sinh of 2t is equal to 2 cosh of t times sinh of t. So let's fill that in. So this here, we're going to write as 2 times sinh of t, sinh of u. It's going to be sinh of u times cosh of u. So we're going to rewrite it that, and then we can throw in and evaluate at our limits. So we finally get what? This 2 and this 4 are going to go to 1/2. So this is going to go to 1/2. And then we have a sinh of t, and then cosh of t. Remember, that's 1/2. Those didn't cancel. They just go to 1/2. I want to make sure we got that right. So we have cosh of t, and then plus we have 1/2 t. 1/2 times t. And then everything evaluated at 0, this is going to go to 0. Sinh of 0, just 0. So we have 0 on our lower limit. And now, what do we have here? This is, remember, our definite integral in purple. But we need to remember, we solved another definite integral in yellow, and we need to subtract what we got from that. So this is going to be minus 1/2 times cosh times sinh. So this is minus, and this is what we got in yellow. 1/2 times cosh of t times sinh of t. All right, and you can see, look, these guys cancel right there. So our final answer after all of that is, here it is, t over 2. So that is a pretty nice answer after all of that. And let's scroll back up and talk about this just a touch. So we found our area, 2b, after all of that hard work, t over 2. And one thing to note about this, I want to show you just how analogous this can be to what goes on in circular trig land. So if I were to quickly, I know this video is getting a little long. If I were to draw out a unit circle here, an attempt at a unit circle, and again, this unit circle has a radius of 1. And if I were to give us this little sector here, or define this as t, then this point right here would be cosine of t, and sine of t. All right. And if I were to show you what is the area of this sector here, what is the area of that? Well, we saw that in the last video. The area of this sector, is going to be, it's just a fraction of the entire area of our circle. So the entire area of our circle is pi r squared, and r is 1, so that's just going to be pi, and then times this fraction of it, which is going to be t over 2 pi. These pi's will cancel, and we're left with t over 2. So you can see a nice, cool analogy between the two here, between our hyperbolic trig identities, hyperbolic trig functions, and circular trig functions. And we are done.